my gosh, you guys, you need to get out of this room. I need to make a video. Get out, 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 out. Well, all right, got those minions out of here. Now let's start our lesson. We've got 10.6, our binomial distributions. Oh shoot, there they are again. Dang it, get out of here. All right, today we're talking about 10.6 binomial distributions. So we talked about binomial theorem yesterday, and this is an application of our binomial theorem. First off, we need to talk about what is a frequency histogram. So it's not your average bar chart. What we have is a situation where you're flipping n coins and organizing the results of that. So we're looking specifically, at least in this exploration, at the number of heads that you get depending on how many coins you flip. So if you had one coin, right, you get either heads or tails. Agreed? So if I asked you, how many times do you get 0 heads? That would be a one-time occurrence. And that's the case when you get a tail. And then right here, this little guy, he is the outcome of getting 1 head, and that occurs 1 time. Now that's kind of weird to think about right now, but as you get further into these histograms, let's say you have the number of coins flipped as 2. So you have the possibilities of getting 2 heads, a heads and then a heads, or you can get a heads and then a tail, or you can get a tail and then a head, and then a tail and a tail, sorry. And you can organize that into a frequency histogram where 0 number of heads occurs 1 time, and that is the case of a tail and a tail. And then the number of heads occurring 1 time in your outcomes would be the head-tail combination right here. So that occurs twice. So you put 2 boxes there. And then getting 2 heads occurs 1 time. So you're counting the number of times something happens in your frequency histogram. When you look at the next histogram, when n equals 3, that means you have 3 coins that you're flipping. So I like to organize it in a manner off to the side before I create my histogram. So you have tails, tails, tails. You can have 1 head and every combination of that. So a head could come second, or your head, could come last. And then move into, let's do 2 heads. So head, head, tail, head, tail, head, and tail, head, head. Just as long as you do this in a nice orderly fashion so you don't miss any. And then last but not least, you have all 3 that are heads. So you organize that. The time that you've got a tail, 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 that means you have 0 heads. That's the 1 occurrence there. The number of heads of 1, so that is right. Let's see, 1 head is 1, 2, 3 times that occurs. And then the number of heads occurring twice are these 3, the next 3, and that occurs 3 times. And then your head, head, head is the case where you have all 3 of them are heads, so that occurs 1 time. So the bigger you get, the more coins you flip. If you take a look now over onto the left side, I give you the full outline of when 4 coins are flipped, or when n equals 4. So all the possible outcomes of that would be you've got one case where you have no heads. That would be this box right here. And then you have, let's see, one head occurs next. 1, 2, 3. Where else? 4. 4 times that you just have one head. And then you count, like you just keep going. So the times where you have 2 heads, 1, I guess I'll erase these ones. Oh, are right here. So you have 6 times that 2 heads occur, and continue on making your histogram. And you can go as many histograms as you want, and you're gonna definitely notice a pattern, hopefully. So, some things that I see, because you guys can't talk back to me, I see the numbers 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and you can probably guess what happens when n equals 5. 1, 5, 10, 10, 5, and a 1. Now you need to think about, why is it called a binomial distribution? Well, it follows binomial theorem. It's actually your Pascal's triangle comes back. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, so on and so forth. All right, so there's a lot happening right there in that first exploration, but let's get into the big concepts, all right? So we're gonna construct and interpret probability distributions and construct and interpret binomial distributions. So, what's a random variable? It's just a variable that is defined by the outcomes of a probability event. For example, x could represent the number showing on a die, right? The possible values would be, that x value could be a 1, a 2, a 3, a 4, a 5, and a 6. And we can define a probability distribution for every random variable. All right, so here is a probability distribution. So it's just a function that gives the probability of each possible value of a random variable. The sum of all, okay, super important, the sum of all the probabilities in your probability distribution has to equal 1. So in this probability distribution for rolling a 6-sided die, you have x, that is the number showing on a die, that's all the possible outcomes, a 1, a 2, a 3, a 4, a 5, 6. And the probability of rolling each of those, because it's not a weighted die or anything like that, would be a 1 chance out of 6 to get the roll of a 1. And the same is true for rolling all of the numbers on a unweighted die. So you can actually take this concept. We're going to talk about a bunch of different diagrams today. So you have a bunch of resources that you can use to tackle these problems in a nice orderly way. So for example 1, we've got let x be a random variable that represents the sum, which is really important for this problem, when 2 6-sided dice are rolled. So to get all my possible outcomes, I make this little chart where I'd say, here's 2, 3, 4, 5. Here's the outcomes of rolling on one die. And my other die would be across the top. 1, 2, 3, 4, 5, 6. So we're talking about the sum, where you technically take your 2 dice and you add the sum together. So you say, okay, what's the total on the die, or on the 2 dice added together? So if you rolled a 1, I'll get my highlighter, a 1 on the first die and a 1 on the second die, you would have a sum of 2. If you It might be too dark. If you hypothetically rolled a 3 on the first die and a 5 on the second die, then your sum would be 8. So this is a quick little diagram to help you get your information into your probability distribution. So below here, we've got our probability distribution. So you've got X, that is the sum of the two dice together. So you have possibilities from 2 is your low all the way to 12. So that's why we go 2 all the way to 12. All right. Now, your outcomes, you're going to count how many times this happens. How many times do you see a 2 in the chart above? And you would say 1 time. And how many total outcomes are there? Well, there's 36 in that box because it's a 6 by 6, so quick and easy. So the probability of getting the sum to be a 2 would be 1 chance out of your total outcomes of 36. So 1 out of 36. And then you move on and you go, when the sum is 3, how many times do you see a 3? 1, 2. So you have 2 chances out of 36, which simplifies to be 1 out of 8. Oops. And you keep going all the way down. Okay, count how many. We'll jump to, let's say, 8. How many 8s do you see? I see 1, 2, 3, 4, 5, which is this 5 right here. So there's 5 chances out of your 36. All right. Now, to make your histogram, your histogram just organizes your probability distribution chart. And some fun facts about a histogram are it's not a bar graph, okay? All these bars are all evenly spaced, so you can't have one bigger than the other, okay? And you must title your diagram. So rolling 2 6-sided dice. And then you need to make sure that you label your x-axis as the sum of 2 dice, and make sure you label your y-axis, your p of x, as the probability. All right, so you need to make sure that your y-axis is also evenly spaced. So you create your own numbers depending on the situation. So we go a low of 1 out of 36 all the way up to a high of 1 out of 6. And then you can organize yourself. Make sure there's no gaps between your bars. And here you go. So you can answer a few questions about this probability distribution here. What is the most likely sum when rolling 2 6-sided dice? So which one most frequently occurs? And you can see that definitely the 7 happens the most, okay? So we'll label it as 7, and that's because it has the greatest probability. All right, and then in the next problem, we can ask, what is the probability that the sum of the 2 dice is at least 10? So what does that mean? That means that we want the sum to be more than 10. Do you agree? Or in fact, including 10 and greater. So we would write this as the probability of x being greater than or equal to 10. And that would just be, looking at your chart, you would just add the probabilities of 10 occurring, 11 occurring, and 12 occurring. Okay, in the notation that you can start to get used to, we're going to go P of x is greater than or equal to 10 is equal to the probability of x equals 10 plus the probability of x is equal to 11 plus your last one, probability of x is equal to 12. So look above, look in your chart all the way up there. What's the probability of x equals 10? I find that right here. What's the probability of x equals 11? Here, this column. And 12 being in that column. So you're going to take that 1/12 plus 1/18 plus 1/36. Add them all together, and that actually works out pretty nice to be 1 out of 6, which is about, I'll take 1 out of 6. I will also take 0.167, and of course we know that as a percent of 16.7%. Be flexible. I'm not sure what the back of the book says. In example 2, we've got a spinner that is divided into 3 equal parts. Let x be a random variable that represents, highlight this, the sum when the spinner is spun twice. Make a table and draw a histogram showing the probability distribution for x. All right, so the sum when it's spun twice. So you flick your spinner and hypothetically you get a 1, and then you spin again and hypothetically you get a 2. So then you add those two together and that equals 3. I like to organize that into my little chart where you've got the sum of your 2 spins. So you could have all the possibilities. You could get a 0 on the first spin, you can get a 1 on the first spin, or a 2 on the first spin. And your second spin would be maybe a possibility of 0, 1, or 2. So when you're talking about the sum, you're going to add these two together. So 0 plus 0 gives you 0. And then you take your next, I'll get my highlighter, 1 on the first spin and a 0 on the second spin, and that'll give you the 1. And a 1 on the first spin will give you a sum. If you get 1 on the second spin, that'll give you a 2, so on and so forth, right? So a 2 plus a 2 on the second spin will give you that 4. And you have a total of 9 outcomes. So let's organize it. When x is the sum, you've got opportunities of getting 0 through 4. So fill that in as your x values, and then the outcomes you need to count. Count how many times did, let me erase a little bit. How many times did you have an opportunity to get a 0? That occurred 1 time, right in this box right here. Okay, so that occurred 1 time. Out of 9 would be the probability for getting a sum of 0. And then moving on, if you see a 1, so a 1 is right here and right here, so that occurs twice. It's got a frequency of 2, so that is 2 chances out of 9 for that probability of getting a sum of 1. Keep going. You've got an outcome of 2, and that will occur 3 times. So 2, 2, 2, right down that diagonal. That occurs 3 times. So you have a 3 chances out of 9, which simplifies to be 1/3. And finish off the rest of that chart. And you create your histogram from there. So your x value is the sum of 2 spins. And then your y-axis would be the probability of that occurring. And the title would be spinning a 3-section spinner. Okay, you've got your 0, that is a probability of 1/9, and then the sum of your 2 spins of being 1 would be 2/9, and then up to 3/9, which is really your 1/3, would be your most frequently occurring sum, and downhill from there. So you'll see that these histograms are really symmetrical. What happens on one side will happen on the other. Okay, so you have a peak and then they fall. So you can answer a few questions. What is the most likely sum when spinning a 3-section spinner twice? So your most likely sum would be a 2. And then what would be the probability that the sum of the 2 spins is odd? Okay, so look back. Which sums are odd? You would have 1 here and a 3. So that's 2 possible outcomes for the 1 and 2 possible outcomes for the 3. So you take the 2/9 probability plus the 2/9 for getting a 3. Add those two together and you get 4/9, which as a percent is about 44.4%. Now we get into binomial distributions. So this is when you're going to be running an experiment. There's many different types of distributions, including normal distributions. Today we're just talking about the binomial distributions because we just came off of Binomial Theorem. So one type of probability distribution is this binomial distribution where it shows the probabilities of the outcomes of a binomial experiment. So binomial meaning your outcomes are either success or failure. There's no other option. Or like true or false. 2 options for your experiment's outcomes. So let's talk about what a binomial experiment actually is. So it's an experiment that has to follow these conditions. You have a certain number of independent trials. We'll call that n. We've got each trial has only 2 possible outcomes. You either succeed or you fail. There's no in between. That's binomial, 2 outcomes. The probability of success is the same for each trial. This probability is denoted by p. So p is always success. So if you're talking about a probability, we know the sum has to be 100%, right? So 100% as a decimal is your 1, right? So if you take the probability of having a success is p, what would be the failure? You take that 1 and subtract the p from it, and you'll have the probability of failure. Right here, 1 minus p. So you've got, for a binomial experiment, the probability of exactly k successes in n trials is probability of k successes is equal to your binomial theorem, your n choose k, probability of success here. I'm going to zero in. There's a lot going on here. So probability of your success is p to the k times 1 minus p, which is your failure, to the n minus k. All right. Now, I have a bunch of information about using your graphing calculator about this. So if you're trying to use your graphing calculator, you can do a lot of this math straight from there. And you would use, here's your keystrokes. Start here. Go second, vars, to get to the distribution drop-down menu. So second vars, and you're going to scroll down all the way to, for this case, when you want exactly k successes, you don't want the sum of a bunch of successes, you're going to use binomial PDF. So that is the discrete binomial distribution function. You're going to enter number of trials, your probability, your x value, and your k value into there, and it'll calculate all of this for you. So use only binomial PDF when you're calculating the probability of one x value. All right. Now, you have to do that a bunch of times usually. So graphing calculator is super handy for problems like this. And if you don't have one, you can do it by hand. So example 3, you've got, according to a survey, about 33% of people ages 16 and older in the US own an electronic book reading device or e-reader. You ask 6 randomly chosen people, ages 16 and older, whether they own an e-reader. Draw a histogram of a binomial distribution for your survey. All right, so we have the probability of success being 0.33. So what logically would be our probability of, so this one's success. What's the probability of our fail? Take 1 minus 0.33 and you get 0.67. So we need to have both of these probabilities. And when we're going to get our binomial distribution here, we need n as 6. If we zero in on just this statement right here, the probability of people having no, so K will be the number of e-readers. If no one said they had an e-reader, that probability could be calculated. So you have 6 choices, and you're choosing 0 of them. So 0 people having an e-reader out of 6 would just be the probability of your success to the 0 power. So this guy always matches this 0. And then your probability of fail is the 0.67 to the 6th power. And that'll be 0.090. And you have to do this for all the different possibilities of how many people having an e-reader. So you're going to see you've got the probability of someone having, one person out of the 6 having an e-reader would be P of K equals 1. So you drop it in to your formula. You got 6, choose 1. Your success, your fail. So you have 1 success, you have 5 failures, and type that into your calculator and you get 0.267. And then the probability of 2 people having an e-reader would be you get 2, out of 6 people, you chose 2 to have success. So here's your success probability, your failure. So you have 2 people being successful and 4 people not being successful. So those are exponents. And you continue this. And yeah, it does take a long time. I apologize. It's not like one of your favorite things to be doing. At that point, you can organize it into a histogram. And your x-axis would be the number of persons who own an e-reader. So 0 people owning an e-reader is fairly probable compared to all 6 people having an e-reader. And you'll see that your 2, the number of persons who own an e-reader, is the most frequently occurring. So it has the highest probability, and that probability is the 0.329, or about 33% of people. So you're probably wondering, how do we shorten up this work? Well, you can use the binomial PDF. So to plug into your calculator, for this situation, for example 3, you would plug in, get to your binomial PDF through second vars, and you're going to enter 6 for your trials, and the probability P is the probability of success. So you would enter 0.3 into there, or 0.33, and your X value, that is I mean, it's a variable change on you, I understand, but in our case, it's the k value. So the x value, if you wanted the x value of k equals 0, you would hit 0 and then paste it. So for your k equals 0, if you were to do that math in your calculator, I pasted that down right here. You would have binomial PDF. 6 is your trials. The 0.33 is the probability, and your x value, which is really our k value here, would be 0, and you'll see this probability of 0.09 right here. Okay, so you could use binomial PDF to calculate each one of these. We're going to use this binomial distribution to answer a few questions now. So what is the most likely outcome of the survey? We kind of already talked about that, but let's take a look. We know that it's 2 because it has a probability of 0.329. So we'll say 2. And what is the probability that at most 2 people have an e-reader? So what does at most mean? That you could have people, like no people have an e-reader, 0. You could have the possibility of only 1 person having an e-reader, or you could have at most 2 people having an e-reader. So we want to take a look at what those probabilities are. So we could write that out as the probability of k being less than or equal to 2 would just be, you're going to add up all the probability of getting a 0, 1, or 2. So probability of k equals 0 is our 0.090 plus probability of k equals 1, which I don't remember off the top of my head, plus probability of k equals 2. So I'll go back up to my diagram, and we're looking at these 3 probabilities that we're adding together to have at most 2 people who own an e-reader. And those are fill it in, 0.267 plus 0.329, and that gives you a probability of 0.686, which is 86.6 as a percent, and I don't care which way you want to write it, as a percent or as a decimal. But you'll also appreciate your graphing calculator for this one because you can actually do this whole part B in your graphing calculator. But because we want to add up these probabilities, we can use what is called the Binomial Cumulative Distribution button. So instead of our discrete PDF, we're doing CDF for the binomial, which stands for cumulative. So if we want, okay, I just rough sketched up until 2, we're going to use binomial CDF. So you're going to go second vars to get to the distribution. It's in the same area as our binomial PDF. It's just one below it, and you're going to hit binomial CDF. So what this does, it sums up all the probabilities up until 2, and it counts always from left to right. So it's counting kind of your left side. It's never going to count the right side, and I'll show you what to do when you have maybe a more than situation. So you can enter the number of trials as 6, your probability of success as 0.33, and the x that you see is the x value that you're telling it to add up until. So you're going to add up 0, 1, up until 2, and including 2, technically. All right, so try that out on your graphing calculator and make sure you get the same probability as above. Here's another example, because this stuff is kind of tough. All right. According to a survey, we have about 62% of adults that have visited a dentist in the past year. Oh, scary thought. You asked 5 randomly selected adults whether they have had a dentist visit in the past year. We're going to draw a histogram of the binomial distribution for our survey. So, your K is the number of adults that have visited the dentist. So when K is equal to 0, we're going to calculate the probability of 0 adults that you asked went to the dentist. So 5 choose 0, plug it into your formula, times the probability of success. And success probability, we're going to use 0.62. So our failure would be subtract 1 minus 0.62, and you get 0.38. So probability of success is 0.62 raised to how many successes did you have? You had 0 successes, multiplied by probability of failure, 0.38, and pretty much at that point, your failure would be all 5 did not go to the dentist, and that'll give you, calculate it out, 0.007%. Now keep going. Probability of K being 1, you would have 5 choose 1. Probability of success is 0.62 for that one person being successful, multiplied by 0.38, your failures. How many would fail? How many did not go to the dentist if one of them went? It's 4. Make sure that your exponents always add up to 5. Helpful hint. 0.064 is that answer. Keep going. K is equal to 2. That means 2 people out of the survey went to the dentist. That probability would be 5 choose 2 times 0.62 to this. You have 2 people that went to the dentist, and you have 3 people that did not. So that probability, 0.211, and you continue this for all your K values. So K equals 3, K equals 4, K equals 5. This guy would be 5 choose 3. Probability of 3 people going to the dentist would be 3 successes and 2 failures. Calculate it out. You get 0.34. My kids are going crazy. So 5 choose 4. 0.62. You've got 4 successes. You've got 1 failure, and that probability of 0.28, and 5 choose 5, 0.62 to the 5, all 5 people going to the dentist. So you've got 0 failing, that probability is 0.09. Wow. So now you get to organize that into a histogram, right? You've got the probability of 0 people going is really slim, of 0.007, and then the probability of 1 person who went to the dentist is your 0.064, and organize it all nice and pretty. And you're like, I don't want to sit there and waste my time. Make sure you're using binomial PDF. So you've got 5 trials. Probability of success is your 0.62. And you go through, just enter them all as an x value of 1. And then hit enter and you'll get the 0.007. And then go back, change it to a 1. And then change it to 2, 3, 4, and 5. And that'll save yourself a lot of time. You can ask yourself, Obviously, what is the most likely outcome of the survey? Take a look. Most likely, you're going to have 3 people out of 5 that actually visited the dentist. So 3 people visited the dentist. Okay. The last problem, we look at what is the probability that more than 3 people surveyed have visited a dentist in the past year. We're looking really for 4 and 5 people who have gone to the dentist, right? Because you're talking about more than, so you don't want 3 or below. Looking at the diagram, what we're looking for is the 4 probability and the 5 probability. So we already know those numbers. We've got the number of adults going, that's 4, is the 0.28 from our data before, and a 0.09 is the probability of 5 adults who have visited the dentist. And really you just add those 2 probabilities together and you get your answer of 0.37. Now if you want to use your graphing calculator to do this, you're actually going to find the binomial CDF of the left-hand side of the distribution because that's how binomial CDF works. It counts from left up until right all those probabilities. It's not going to find you this like complement of 4 and 5. So we're going to jimmy rig it a little bit and go and understand that all those probabilities add up to be 1. So we're going to just take 1 minus the binomial CDF of up until 3. Okay, so we're going to use the trials as 5, your probability of success as 0.62, and it'll count from 0 all the way through 3. And you'll end up with the same answer of 0.37. All right, and we're done. Yay!